everyone. My name is Seunghwan, and today I will introduce a paper titled HYBGRAG Hybrid Retrieval-Augmented Generation on Texture and Relation Knowledge Bases, which was suggested at ACL 2025 main conference. This work aims to improve question answering by combining texture and relational information. There are three representative types of question answering benchmarks. First, open domain question answering. ODQA focuses on questions that require unstructured text sources like Wikipedia or web, and it typically uses a text retriever to find relevant passages. And second, knowledge-based question answering. It uses structured knowledge bases such as Wikidata or Freebase to reason over entities and relations, and it relies on a graph retriever to explore those connections. And last, hybrid question answering requires both texture and relational information to answer questions. However, most current RAG systems focus on either texture or relational data, not both, so they struggle with hybrid questions that require integrating the two sources. Let's first compare RAG and GraphRAG. RAG retrieves unstructured documents and is mainly used for ODQA tests. In contrast, GraphRAG extends its idea to structured knowledge bases and is typically applied to KBQA. But real-world questions often need both texture and relational knowledge, which neither RAG nor GraphRAG alone can handle effectively. So this motivates HYBGRAG, which integrates both retrieval models to better answer hybrid questions. As you can see in the example picture, RAG focuses only on the texture aspect, while GRAG focuses only on the relational aspect. However, some questions require understanding both. For example, combining textual descriptions from documents with relational links from a knowledge graph. Therefore, HYBGRAG aims to answer such hybrid questions by integrating text retrieval and graph retrieval within a single framework. So before moving on to the methods, the authors identify two challenges in HQA. The first challenge is hybrid sourcing questions. As you can see in the table, the two retrievers, text retriever VSS and graph retriever PPR, perform similarly overall. However, they find different answers since each focuses on different types of clues. This means that hybrid questions cannot be fully solved with only a single retriever, and it is necessary to leverage both texture and relational information to answer them effectively. And the second challenge is called refinement required question. In this setting, LLM, specifically Claude 3 Sonnet, is used to extract a subgraph from the knowledge graph that contains the target entities. If an error occurs during this extraction, an oracle provides the feedback pointing out the error part of the subgraph. This shows that LLMs need a self-refinement mechanism that allows them to improve using feedback. So there are three types of feedback. NA means no feedback is given, and simple feedback such as your answer is wrong, like this feedback, and finally corrective feedback, which gives a more specific hint. For example, the entity in this section is incorrect. Let's move on to the methods section. The author designed HYBGRAG framework mainly to address the two challenges we discussed earlier. So hybrid sourcing questions and refinement required questions. To tackle this, the model is composed of two key components, a retriever bank, and a critic module. First, the retriever bank is designed to handle the first challenge, hybrid sourcing questions. It consists of multiple retrieval modules and a router. There are two types of retrieval modules, the text retrieval module and hybrid retrieval module. The text retrieval module, which searches unstructured text documents using similarity-based methods such as dense retrieval, and the hybrid retrieval module, which is slightly more complex. It first extracts topic entities and relations from the query, then uses a graph retriever to collect related entities within the ego graph. Finally, it ranks documents connected to those entities using a VSS ranker and essentially combining graph-based retrieval with text ranking to reach structured and unstructured information. The reason why they didn't utilize a graph retrieval module alone, it is because text retrieval module generally perform higher than graph retrieval module, so they indicate that they use only text retrieval and hybrid retrieval. And the router decides which retriever to use for each question, text and hybrid retriever. It identifies whether the query is more relational or textual by analyzing entity and relation types, and then dynamically select the appropriate retrieval module, either text or hybrid. This routing process also interacts with the critic module at later, which provides feedback for improvement. And I will introduce the critic module, which is solving the second challenge. The author proposed the critic module. This module enables the system to self-reflect and refine each retrieval process. It consists of two subcomponents, a validator and a commenter. The validator checks whether the retrieved contextually satisfies the question. If the validation passes, the system outputs the final answer. They generate the final answer. If not, the commenter provides feedback to the router, and router do work again. This feedback can be corrective, specifying which part of the retrieval was wrong. For example, an incorrect entity, a missing relation, or a wrong retrieval module. The commenter uses in-context learning ICL, referencing around 30 successful examples to generate high-quality feedback. This feedback loop allows the system to improve its routing decisions through self-reflection continually. In this paper, they didn't provide the overall pipeline, so I make a simple overall pipeline. From query router extract the entity and content. So router pick text or hybrid retriever 1, and that retriever get top K references from outside, and using these references, the validator give true or false answer, and if false, the commenter made a feedback, and this feedback go to the first part, and router pick text or hybrid retriever again. The router, validator, commenter is all utilized as Claude 3 sonnet. So the authors, and I will explain the experiment. The authors evaluate HYBGRAG mainly on two hybrid question answering benchmarks, Stark and Crag, to verify both each retrieval performance and end-to-end reasoning ability. First, this table shows the retrieval evaluation result on the Stark benchmark. We can see two datasets here, Stark Mag and Stark Prime. Both datasets utilize semi-structured knowledge bases, SKB, that combine structured knowledge graphs and unstructured text documents. However, the key difference lies in their domain complexity and how that affects the model's performance. Compared to all baselines, such as dense retrieval, BSS, and even graph-based retrievers, HYBGRAG achieved the best performance across all metrics. This clearly shows that integrating texture and relational retrieval improves the ability to find relevant evidence. Next, the authors conducted several evaluation studies to analyze each component. In the design choices section, we can see the adding commenter feedback and validation content significantly improves performance, showing that feedback-based refinement is effective. In this also, and in the self-reflection plot at the bottom, as the number of refinement iteration increases, the retrieval accuracy hit one consistently improves, demonstrating that the system indeed learns from its own feedback. Then the authors also test different model size and multi-agent settings. When using Claude 3 Sonnet instead of Claude 3 Haiku, the performance increases in all metrics despite slow inference speed. And importantly, the multi-agent version of HYBGRAG, whether the router, validator, and commenter interact, performs much better than single agent or no agent versions. This highlights the benefit of collaborative refinement among agents. And finally, this table shows the end-to-end evaluation on the complex RAG benchmark. Unlike the Stark benchmark, this focuses mainly on the retrieval ability for hybrid question answering. The CRAG benchmark is a complementary evaluation designed to assess the overall RAG performance, covering both ODQA and KBQA as subtasks, while Stark primarily evaluates the ranking quality of retrieved evidence. CRAG focuses on the accuracy of the final generated answer. According to the result, HYBGRAG outperforms all other baselines, including COT-LLM, text-only RAG, graph-only RAG, and React. So that is demonstrating its superior ability to combine texture and relational reasoning in a unified RAG framework. So in conclusion, HYBGRAG demonstrates several key advantages. First, it is agentic. The system can perform self-reflection through the creating module, allowing it detect to correct its own retrieval errors. Second, it is adaptive. By using the retriever bank, HYBGRAG can flexibly handle different types of hybrid questions that require both texture and relational knowledge. Third, it is interpretable. Since the refinement steps are intuitive, we can clearly understand how the model improves its reasoning and decision making. And finally, it is effective achieving SOTA on all HQA benchmarks tests. However, there are some limitations. The model currently uses relatively simple retrieval method, so there is room for optimization in retrieval quality. Second, the domain adaptation ability is still limited. Performance may vary depending on the dataset or topic domain. Lastly, the in-context learning examples are randomly selected, so there's potential to improve further by controlling the experience selection process. So in summary, HYBGRAG provides a promising direction for hybrid question answering by integrated text and graph retrieval, and it enables self-reflection through agent collaboration. Thank you.